Okay, hello. We present the project Deep Dive into Multimodal Embeddings. Our team members are Kirill Tashuk, Anton Zavekin, Maxim Kurkin, Polina Karpikova, Andrew Spiridonov, and Anastasia Pretana from DL course. So the first part of our presentation is about the analysis of the multimodal embeddings, about isotropy, whitenings, and transforms. So what is the motivation behind this research? The motivation is the following. Some papers told us that embeddings of the models like BERT are often anisotropic. It means that they are not uniformly distributed in the space. If you look on the right picture, you can see the word-to-vec embeddings, and the origin is here, and the embeddings are all around the origin. So in whatever direction you look, you will see embeddings, and that means that their distribution is isotropic. Whatever direction you will look at, you will see kind of the same picture. And on the left picture, you can see the embeddings from the transformer model, and they are distributed in a narrow cone. So the origin is here, and all of the embeddings are in a cone. So the directions of the space are not the same, and the embeddings do not occupy all of the space around the origin. Some papers show that this leads to the degradation of the performance of the model, so it does not use the space very efficiently, and some techniques that regularize the model or restore the isotropy can actually improve the quality of the model. So we wanted to study the CLIP model, which is the multimodal model. It has a part that encodes the text and the part that encodes the images, and it is trained by contrastive loss in such a way that the cosine similarity between the text and the corresponding image is more than the cosine similarity between random text and random image representations. So we studied the embeddings, we pre-computed them on the COCO dataset, and here on the right plot you can see that the two distributions of the cosine similarities between random pairs of images and text and between corresponding pairs of images and their captions are different, and they are separated. Also, the cosine similarity itself is not that large, much less than 1. You can clearly see that the two distributions are separated. That is the way that the CLIP model is trained. So here we visualized the distribution of the embeddings using the SVD. So we took the metrics of the embeddings, took the first component and the second component of the SVD. This is the origin, and so projected it into the 2D space. This is kind of the default way of visualizing the embeddings in a linear way. So see here we also can see that the embeddings are in a cone, so they are not uniformly distributed around the origin, and so the CLIP embeddings are kind of anisotropic. Here you can see the distribution of the singular values. You can see that the first SVD component contributes to the major part of the variance of the data, and other components do not have that high of a contribution. And also we computed the isotropy matrix I1 and I2 presented in some of the papers. The I1 metric is from 0 to 1, and the higher the better, and I2 metric is just positive, and the lower the better, the lower the more isotropic it is. And it is actually better than in most of the BERT models. So we can see that although the embeddings are also in a cone, they are not that anisotropic. So after that, we centered the embeddings and then took the first two components. So on the last plot, the first component just measured the fact that the embeddings are not concentrated around the center. And now, so if we look at the cluster of the embeddings, we can see the situation better. And here we actually see that the embeddings are much more isotropic if we look at them this way. And this is a good way to look at the embeddings, because when they are normalized, the cosine similarity is equivalent to distance. They can be represented one through another, and so we can look not only at the angles between vectors, but also at the Euclidean distance between them. And here we can see that the cluster of the embeddings is quite isotropic, and even the isotropy metrics are perfect on it, and the singular values do not fade away that quickly. Some papers also report that the embeddings of BERT models are locally isotropic. That means that if you cluster them, then each cluster will be isotropic. But here we can see that even the whole one cluster of all of the embeddings is already quite isotropic. And finally, we employed the whitening transformation, which takes the PCA or SVD components and equalizes the variance of all of them, making the singular values of the matrix of the embeddings just ones. So all the singular values are ones now. And also we can reduce the number of components as done in PCA. We reduce the dimensionality from 512 to 128. And we can see that, of course, now the clouds of the embeddings looks like a ball, and the isotropy metrics are also perfect. After that, we can also measure the variance of all the coordinates, and we can see if the variance is very peaked. So that means that all of the components have approximately the same variance, and so all of the coordinates of the vectors contribute the same to the distribution of the embeddings. That means that distribution is isotropic, and that's what we expect after the whitening transform. And before the whitening transform, you can see that the distribution is not that peaked, and that the centered embeddings are more isotropic than the uncentered. All of the above results were measured on the distribution of the embeddings of the images, but on the text embeddings, the plots are almost exactly the same. So the results are also the same. And we can see that compared to the BERT models, the isotropy is better. So after that, we visualized together the embeddings of the images and embeddings of the text, and we can see that they're clearly separated. Although the clip is trained in such a way that the embeddings of the image and the corresponding embeddings of the text are close, they do not have to be at the same point. Because the clip uses contrastive loss, which measures kind of the relative distance. So if the embeddings of the image will have the embedding of its caption closer than the other embeddings, then the clip loss will be small. So the 2-point clouds do not have to coincide, but they do have to maintain a kind of relation between each other. And so we can see that this distribution consists of two different distributions, and the isotropy metrics are not perfect, of course. We can also look at the centered, like joint distribution, and also see the two separate clusters, and the isotropy metrics are already perfect. And we can also use whitening, and now the distribution looks more like a ball. The points are still separated because whitening is a linear transform. It cannot mix two clouds of points. But we look in such dimensions, such two components of the 500 or 128 dimensional space, that we see them on top of each other, and the isotropy metrics, of course, are perfect. Okay, so that was just some visualizations of the distribution of the embeddings of images and text by clip. So after that, we thought how we can make the embeddings better other than with whitening. So there are actually known linear algebra problems that make 2-point clouds coincide with each other. There is the orthogonal Procrustes problem and the least squares problem. So the least square problem just learns a linear transform, which transforms one point cloud so that it is as close to another point cloud as possible. And the orthogonal Procrustes problem is the same, but with the constraint that the matrix of the transform is orthogonal. So you do not stretch the points, you only rotate them. And so we hypothesized that we can learn the least squares transformation or the Procrustes transformation and transform to the text embedding closer to the imaging embeddings. And then the model will perform better because the clip exactly learns the embeddings to be close to each other. And if the transformation is orthogonal, that means that the angles between different text representations are preserved. So all of the semantic meaning of the text that clip learned will be preserved. It won't get mixed up. And so we see that on the left plot are the distributions of similarity scores before the transformation, and on the right plot after the transformation. And we see that they are much larger. So after we transformed the text embeddings closer to the image embeddings, they are indeed closer one to another. But we can see that unfortunately the overlap between the two distributions of similarities between random pairs and similarities between the corresponding pairs is a bit more. So probably the quality of our model is a bit less perfect. And this is the visualization after the our rotation of the text. We can see that now the 2-point clouds are on top of each other. And the same plots for the least squares problem. This plot is more or less the same. And here we can see that the text point clouds got squeezed because the transformation is no longer orthogonal to get closer to the embeddings, image embeddings point clouds. And yeah, the SVD plot is more or less the same. Okay, so after doing all these transformations with visualizations, we needed to measure the quality of the obtained embeddings. So the first proxy to the quality is just the clip loss. So we took the COCO dataset with embeddings of images and text, did various transformations, and measured the clip loss again. And we found that, unfortunately, all the transforms increased the clip loss, but that is probably to be expected because the clip embeddings are trained in such a way to minimize this loss. So if we add any linear transformation on top of it, then probably the loss will grow. And so the more interesting task to try to complete is to measure the zero-shot capability of the transformed clip model. So the clip model is famous that we can just encode any image, encode some prompt, like for example, low resolution photo of a cat, where cat is any of the 100 classes present in the CIFAR. And by measuring the similarity between texts and between images and such prompts, we can perform classification without training on CIFAR. And so we measured this capability of zero-shot classification after all of the transforms. So the default clip achieves accuracy of 63%. And these are the results after all of the transformations. And we can see that, unfortunately, if we want to preserve the zero-shot capability, so if we do not want to use any of the CIFAR data for training, we can learn the Procrustes transformation or whitening transformation or LSTSQ, least squares transformation on COCO data, and then use it on CIFAR. So our model has never seen CIFAR. And then the quality drops. So unfortunately, if we fit for COCO captions, we break the relation between CIFAR image embeddings and CIFAR prompt embeddings. The quality drops. We can also use the training split to learn the Procrustes or least squares transformation. This is a bit cheating because it is not strictly speaking zero shot anymore. So we do not use any fine tuning. We do not use any SGD, but we use the CIFAR training data to learn the parameters of the transforms. And we can see that after the least squares transforms, the accuracy actually increased. So if we learn to transform the CIFAR prompts closer to the CIFAR images, then the accuracy of the classification increases. And also, we studied the whitening and the compression. So the whitening compresses the space while also making the embeddings more isotropic, and the PCA just gets rid of the last some components, and so just compresses the data by orthogonal projection. And we can see that the whitening does not hurt the accuracy too much, but also the accuracy, but still the accuracy drops. But when doing PCA, we can actually both reduce the dimensionality of the embeddings and even get a little accuracy increase. Of course, this is not very statistically significant data, but we can use we can see that, of course, the 512 dimensional embeddings used for classification of just 100 classes are probably too much. So we can reduce the dimensionality and even maybe gain a little accuracy increase. And lastly, the last problem that we wanted to solve, to investigate, is can we learn to make the CIFAR image embeddings and CIFAR text embedding closer to each other by learning on the first, say, 50 classes, and then to test will the other 50 classes also get closer to their embeddings. So we took the image embeddings of the images corresponding to first 50 classes. We took the prompts, like low resolution photo of a dog. We made them closer by using, for example, a Procrustes transformation, and we wanted to see whether the images corresponding to other 50 classes will get closer to the prompts corresponding to other 50 classes. And unfortunately, the results are negative. So this transformation, it increased the accuracy on the first 50 classes, but it dramatically decreased the quality on the other 50 classes, probably because even if we do something good with the 50 vectors corresponding to the first 50 classes, we may break the other 50 vectors corresponding to other classes. Even if we use only orthogonal transformation, we have still a lot of degrees of freedom to mess up the other regions of the space. Okay, that is the end of our first part.
So the second part was a study of possibilities of multilingual clip models. As Kirill said, there are some common techniques how to train a clip model to align embeddings of a text, caption, and an image. But what if we use captions from different languages? The most straightforward way is to train a different clip model for each language. For example, there is a RuClip model, which is trained on Russian corpus, but it is not the optimal way, because in this case, we should perform this time-consuming and very computationally expensive procedure for each language. The idea is to use some large language model, which is trained on multilingual corpus as a text encoder for clip. However, to create the appropriate data corpus, we should somehow either parse the data for cross-lingual data set or use machine translation to translate captions from one language to another language or another couple of languages. Then after the translated data set is combined with the original one, we can align the obtained embeddings from the language model in such a way that the embeddings from the new languages will be as close as possible to the original language embeddings. However, as we minimize some kind of loss, for example, the MSE loss, or we can use something else, still there is no appropriate metric on how to measure the quality of textual embeddings besides the actual usage of them to see how good the generated embeddings are aligned with the image embeddings. So we decided to take a look at some embeddings from a couple of languages to see if the point clouds of textual embeddings in the clip space are aligned after that kind of procedure. So speaking of the results, next slide, please. We used a wiki caption dataset, which consists from 1,000 pairs of captions from Wikipedia images, and it has 3 pairs: French English captions, German English captions, and Russian English captions. Unfortunately, the English parts of these pairs are not the same, so we can't perform appropriate cross-lingual comparison of the multilingual clip embeddings, but we can still do it in each pair separately. So as we are not that much interested in linear behavior of clip embeddings, we decided to use the UMA projection technique, which tries to approximate the relationship between data points in high dimension with some local manifold by conserving the local distances for each data point between itself and its n nearest neighbors. So in this case, we can see the general behavior of locality in the data set in high-dimensional embeddings of language of captions in different languages in our case. So we use the UMAP to project the text embeddings for each pair and observe that first of all, the point clouds align visually very well. That represents a good mixing of them, so we can use them interchangeably. And it proves that the proposed technique of obtaining multilingual clip models works well enough, so we can use the captions from different languages interchangeably, given the fine-tuning procedure of training the large language model to obtain the clip embeddings is performed well enough. And we also calculated mean distances between each pair of points from different point clouds. We can see on the next slide that this data allows us to understand if the relationship between 2 point clouds is some representation of high-dimensional data, good or not. For example, the ratio of the ratio of the mean pairwise distance to the mean global distance, which represent the characteristic size of the point cloud, is quite low. That means that even in high dimension, the point clouds of embeddings mix well enough, because otherwise, if the ratios were higher, then that would just mean that embeddings of each given sentence are close to each other, as one of the embeddings was obtained from another by some kind of language translation performed by a neural network. But in the clip space, after proper fine-tuning, not only each embedding of a sentence in one language corresponds with high accuracy to this embedding of the same sentence in different language, but also the point clouds representing the whole data correspond to each other very well. So the multilingual clip, as it was proposed to be fine-tuned and used, works quite well, and the quality of the textual embeddings provided by this model is rather high. So that's it. Thank you for your attention. If you have any questions, we will answer them in the chat or by the email.
Thank you.